Excellent. So how many people here have ever built a model before, like in scikit-learn, TensorFlow, anything like that? Actually, like built a model, did the scoring job, played around with it. Yeah. So today I'm not doing an LLM presentation. So thank you very much. Thank you. How do you actually move from more of the traditional batch learning that most of us are familiar with, gathering a whole bunch of data up, building a model, maybe scoring it once a day, once a week, once a month to make some type of decisions, and actually get into event-driven, real-time, predictive AI. And if you think about like how this is different, when we have our batch data that we're getting from our data engineers and people like that, we might get it on some type of regular schedule, like we get nightly dumps, weekly dumps, things of that nature. Sometimes a lot of like the time and like the order these things occurred is just missing from us. It's been stripped out through all the processing. It was never really there in the first place. The data is still frequently coming from like lots of multiple aggregate sources. You've got some data engineers who've built some nice transformations for you. But at the end of the day, you're building these models to make batch-based decision making. So what we're going to talk about today is a little more of the theory of how to do event-based model training and scoring. So with events, these things, we want them to arrive real time, like right as they occur. Like if something happened, we want our model to be able to know about it in like fractions of seconds, potentially. These events in life, they occur in some type of order. There's meaning that we can derive from that in model building. We're still going to want to get everything from all these multiple sources. But at the end of the day, because all of this is real time, you as like a data scientist, you're going to be responsible for really aggregating and transforming all these events into meaning, because you're not just waiting for a batch or some data engineer to stitch it together for you. So if you think about like what's our process when we build predictive models, we tend to collect our data, we do our feature engineering, we train, we refine our models. We kind of do that in a feedback loop, trying to come up with more and more features. We select our models, we promote an MLOps, and we collect performance. How's this different when you're working with event data? Where you're not dealing with just like big batch tables, but just discrete events. What do your features look like? What does your model training look like? And that's what I'm going to kind of go over today. So, kind of as like a practical example, I want you to think of an automated warehouse. I don't know if you've ever seen one of these monstrosities where they've got all the conveyor belts, the robots, the pickers. Like every single device in this warehouse creates tons of events. You've got your motors on the assembly, you've got your motors on the conveyor belts. They'll tell you their temperature, their torque, their vibration, all the voltage spikes, everything like that. You've got all of your robots that are actually like grabbing SKUs off of the various layers of all the inventory, pulling it down. You've got all of your temperature sensors. And all of those things, those represent events. Those are every single second that goes by, minute that goes by, that's data, that's information, those are events. And you need to be able to aggregate all those up into something that can handle that scale. And then you're able to actually be able to build models off of it that are real time. The other thing is you're probably going to want even more data than just that. You may want, for example, the maintenance information on all this stuff. So there may be a maintenance ERP system, and every time there's a change in that, you want that to be an event in your stream as well. So like when somebody goes and repairs a system or changes something on the floor, that's an event. So you need to aggregate all of these things together and collect them. That's where event streaming technologies like Red Panda and Kafka help, because you can get all this stuff in one place. But now that you've had those events, what are you going to do with them? How are you going to turn that into like actual features that you can use to train and build models? So there's a lot of tools out there. There's things like Faust, there's things like Flink, stuff that is able to take all these pieces of data, and you can create like lag features, maximum features, minimum features, variance. You can even do delta features between different topics. And in the essence, what you're doing is you're taking what would normally be like a batch of data, you wait for a whole day or week or whatever to get, and turn it into a snapshot of time, something that represents a few seconds of reality. And more importantly is you can correlate all this data across different things. So, my motor that's sitting here running that conveyor belt has another motor next to it that's also giving me data. Well, that's a multiple series of data. And now that you have all that real time, you can do things like multi-series, cross-feature engineering, where you're actually looking at information from one motor into the other to determine the probable cause of why something might break. Just because this motor is struggling doesn't mean that this is the motor that's actually going to break. It could be struggling because the motor downstream from it has stopped putting out the appropriate amount of torque on the belt. If you're only looking at one individual view of reality, you can't figure these things out in your models. And so this really represents a much different way of building predictive AI, because instead of just like making long-ranging decisions, you're trying to get as close to current time and reality as possible. The things that you do with this are still very similar to traditional data science. You're going to build your features. You might even use automated feature discovery software to help with this. And you're going to build your code. And at the end of the day, you're going to train models. You can use all different types of things to train your models with this data. You can use scikit-learn. You can use your data IQs, your TensorFlows, Prophet, everything. But it's an iterative process all the same. You are just using real-time data rather than batch. And you're going to iterate. You're going to use all of your things like feature importance, rank ensembling to figure out which are your best features, which features are actually giving you the most signal, which ones are the most computationally expensive. Maybe I don't want to use those. It's just basically very standard data science at the end of the day. Events are time-based by nature. So when you're actually building event-driven models, you're always in the space where you're trying to build time-aware models. This isn't just like a large batch file where you're going to predict things, like, will this person leave the hospital if I don't treat them correctly? What you're really looking at is very time-based features, where because all of these things are happening right now, what's likely to occur with this particular element. And because of that, the way that you actually have to train your models and select them is a little bit different. You can't just use old methods like cross-validation. You need to use stuff like backtesting and build entire collections of models and kind of put them through multiple survival fitness tests as you move along, so that you arrive at models at the end of the process that are more adaptive and can handle change and can deal with sudden alterations of the types of data that's coming in. Because if you just simply train and take your absolute best model over an entire period of time, you'll find that while it will claim it has really good accuracy, the minute you put it out into the real world, it will not, because it hasn't actually gone through that gauntlet of survivability over time. So you need to have things that you have to consider your lags for your features. What is a reasonable lag period? For this warehouse example that I'm telling you about, your lag period is probably going to be something like a little bit of buffer of how much time it takes me to get all of that data in one place and properly process it. That's probably my first lag for all of my features. And then I'll probably build additional lags and everything like that. But you're generally restricted by how quickly you can assemble your data. And that's why you need a really good real-time message bus that can pull all this stuff together quickly, and tools like Flink, things like that can actually process it really quickly. You still have to do a lot of stuff like impute missing values. What happens when I've got my model running and some of my features don't show up because something's broken? I'm just simply not getting that data out of the sensors at the moment. How do I make my decision then? So again, your models have to have the ability to do things like impute missing values, because you're working in the real world now. You can't just fill them in, and spend a lot of time thinking, how am I going to go back, get the right data, correct the data, and then rerun it, because you don't get to rerun the job. You get one chance. So going back to that, like, warehouse, what would be like a useful model for a warehouse? Like, what's the probability for each component in my entire warehouse that it's going to break down in the next 30 minutes? This is the type of thing that you can do with real-time data that you can't necessarily do with like a batch operation. And at the end of the day, how am I going to implement that? In MLOps, your considerations for how you do a real-time model, you're going to need to use the same transforms in production that you used in your training data when you built your training regimen, which means that your transformations have to be lightweight, quick, they have to be able to finish in time. So that's something that you have to really think about while you're building your models is, can I run this in production? Will it finish in time? Can I maintain these time periods? And your data may not arrive in time. It may be late. And your model has to be able to handle missing data. And typically what this means is that it usually is helpful in MLOps to actually run multiple models. You don't just rely on one model for this decision. You probably have some more complex models that are more accurate. If they finish, that's great. You probably have some more simple regression models that are likely to be able to finish in time regardless of what happens. And at that point, what you need to do is you have to do things like layer on a decision engine. What am I going to do when I'm given all these different inputs from all these different models? What decision am I going to make? And how you weight those things. And at the end of the day, you also have to capture all of your actuals. What happened? Did the machines break down? All those are events. They go back into the queue as well so that you can evaluate your models, determine their real-world accuracy, and see what your drift is between all of your various features and your accuracy. So the nice thing is that because we already have an asynchronous message queue for that, we can use it for all these MLOps purposes too. Features get transformed, they go into the message queues, models listen to those queues, take those materialized features, make predictions, predictions go back into the queues, dashboards view the predictions, decision engines use the predictions. We have this nice loose coupling where most of the time everything will work, messages will arrive in time, but if they don't, you usually want to engineer a few stopgaps around that. Do you fail open, fail closed, all those sorts of things. So I'm going to kind of show some of like how this might potentially be put together in a very simple, but not a particularly practical demo. I'm going to tell you this is not a really cool model. It's not super accurate, but it's going to underscore some principles that's going to help you kind of gel some of this stuff in your mind. So what I'm going to do is I'm going to just build a small little model that's going to guess how many planes are in the air in the next hour. So what can I get for data streams for that? Like from public APIs, I can get the current flight data in the US, just like planes in the air. I can get that from an API. It's free. I can get the current weather conditions in major cities. That's free as well. But current weather conditions may not be as helpful to me as, say, forecasted weather conditions. Now, I know the forecast data is inaccurate, but I can use that because that's information about the future. It might not be perfect, but I will know that at the time of scoring. So my goal then is to try to accurately predict how many planes are in the air 1 hour forward in time. Notice one of the things missing from this, I didn't take the plane schedules, that's too easy. So if you have the actual plane scheduling data, it's helpful, but didn't want to do that for this. And now let me X out of it. We'll get back to this slide in a moment. So if you think about the data itself, so I need all the US flights. I actually put those in a CSV because it takes too long to read that stream over the internet, like from this little room here. How do I prepare that data? How do I take all those plane events and turn it into something that I can build a model off of? So I can take that data, I'm going to remove all the flights that aren't actually commercial flights. I'm just going to deal with commercial flights right now. I'm going to convert the position time of when that plane last reported itself. I'm going to take the average of the altitude, because I'm just going to use that as a feature later. And I'm going to fill my missing values where planes didn't put out their altitude as a mean. This is just like a fudge that you do in data science to try to kind of do a no-op of sorts for when you're missing data. So that gives me all of my flight information as it currently exists. But these planes report multiple times per hour where their current position is. So I'm going to resample this data in a rolling 1 hour window, only keeping the last time the plane reported its position. So this is going to basically give me kind of a snapshot at the end of the hour of where the last known presence of all these planes happened to be. Could have been on the ground, could have been in the air, etc. And so I resample that data, and then I can take aggregates of it and figure out how many planes were in the air for each particular hour. Oops, grab that. And I'm also going to just take average altitude as a feature. Maybe like the average altitude of all the planes in the air kind of can give me some signals to whether the planes on the whole are going up or going down. Might be a good feature, don't know. But we're going to try that. And so then I write all that data back to my queue. So now it's back in Red Panda. It's in its own topic. It's in its own topic called Aggregate US Data. Like if I look at my topics list, I've got a bunch of topics here. I just ended up writing it all back to a new topic. Now I have aggregate data. But what if I want to enhance that a little more? Maybe I want to use like some weather data. So I can take the current weather, go through the same process as I did before, read the data in from the weather queue. You can kind of see what the weather sort of looks like. I'm going to flatten that JSON into dictionaries, get it into pandas. This stuff I did in a notebook, so you could kind of see what's going on. Normally, you kind of do this in Flink or Faust or something like that, runs this backend service. You wouldn't really be able to see what it was doing at all. So what I'm going to do now is I'm just going to say, well, it's windy in Chicago usually. Chicago is like one of those airports that loves to disrupt air traffic. So I'm just going to say, okay, I'm going to measure the wind speed in Chicago. And that's going to be something that I keep for my weather. And I write my weather in Chicago back out to the queue in 1 hour increments of where it was. So now I have my flight data. It's in queue. I have my Chicago weather data in queue. So now what I'm going to do is say, okay, if you are, I get all my flight data resampled again because I have to have it sampled. And what I'm going to do now is I'm going to say, okay, well, if you're within 100 nautical miles of Chicago, I'm going to count you as a plane that's near Chicago. And if you're not, I'm going to count you as a plane that's not near Chicago. Again, just creating another feature to enhance the overall data set. And so now I have my column where I've got my planes that are near Chicago. So I put my aggregate together. And so now I've aggregated 2 different data streams with real-time data, fixed all the windows so they're compacting down to 1 hour increments, aggregated it all together. I've got my average altitude, how many planes are in the air at the time, what the wind speed in Chicago happens to be, and the proportion of planes that are actually near Chicago, meaning they're within 100 nautical miles of it by longitude and latitude. And I write that back out to my queue. So now I've got this queue of all these features that I've pulled together. I told you this is not a particularly practical demo. Obviously, there's a lot of better features a person could make here. But these are easy and quick. And if I go then to, say, Google Colab, I can install Prophet and the Kafka client. Let's give that. It likes to reset my entire session every time I'm idle for a while, but I've used Colab before. It's very ephemeral. It deletes everything. And now I'm going to connect to my Red Panda server using the Kafka library. I'm going to create a consume polling loop that just goes and reads from the queue, looks for the data, gets it out. So you can kind of see I've got the same data here that I wrote to that topic. Let me give it a moment. Oh, yes, the classic. Okay. What did I do? What did I do? All right. Classic problem where it breaks. Oh, you know what? I know what I did. I didn't actually run mine. I cleared this out in order to prepare for this. And I was actually planning on running this one in order to populate the queue. Sorry about that. And I'm bad with an Apple touchpad. So we're going to run this one. It's going to go through, do its magic, write everything out to the queue. And that will take a little time. And so since that's going to take just a little bit of time, let's do like maybe 1 or 2 questions while that one's running. Okay. Where we have one? Yes.
You can't tell if you're training your model in real time or how do you train your model and make sure the model is reliable?
Yeah, so what you do, I think
Turn back my off.
yeah. So the question was, are you training your model real time and how do you tell if your model is still reliable? So what you're doing when you train is you actually play forward these windows over time and create all of your features, and you train time-based models. So like, for example, you're going to do your predictions, and instead of doing like cross-validation, you do back testing. You say, I'm going to take like 21 days and just run this simulation forward, and then score how accurate the model was. And like of the hundreds of models that you build, you drop the percentage that are the least accurate, then you do that again, and then you do, but you give them the first 21 days that they just did because you're allowed to retrain with data as it comes in. And that's how you build your initial model set. And then what you do is when you put them into production, you score each hour, and then it's kind of a choice whether you want to retrain or not using that last hour of data that you got before you score the next hour as time marches on. And usually you'll make that choice based on whether you've seen your accuracy dip past a certain threshold. You'll decide to take the compute cost to do a retrain before the next scoring window. So if you see, we have written out all of our new data. It is hopefully over there now. And as you can see, I wrote that out to the queue. It's out in my Kafka, in my Red Panda servers, reading it via Kafka protocol. Coming back down to my Colab environment here, I've got my timestamps, my average lags, my wind speed, etc. So went up to the queue, went back from the queue. I can now train a model in Profit. Model's trained. And now I can score, 1 period into the future with it. And voila, my model now thinks that there'll be 5,818 planes 1 hour from now in the air. So that's kind of how you do that. Obviously, you probably want to use shorter and shorter windows as you refine things, get your system running, etc. But that is the essence and the framework of how you approach doing real-time scoring and training versus these legacy batch algorithms you're mostly used to. I think I got about 3 or 4 minutes, I think, for questions.
Yeah. Yeah, we have to go ahead.
I was curious, a lot of the examples you were given, I kind of was getting a mental model that you were interested in predicting things that there might be extremely few events over the course of the factory lifetime, like certain types of failures. So if you were trying to assemble a data set, you only had zero, 1 or 2 of these things, it'd be very hard to train a model. So I was wondering what kind of models you had in mind for those kind of things.
Yeah, if it's not a, hold on. Yeah, this is working. Yeah, if it's not a model where you regularly have breakdowns, you're not going to get a labeled data set. So typically with that sort of thing, you would build a anomaly detection time series model so that you're actually reporting on things that are occurring that seem outside of the ordinary, as opposed to necessarily I'm going to predict a specific failure. Because if there's not enough of a history of failures to label a data set like that, then you typically get into the anomaly detection area where you're going to do like multi-series anomaly detection in the entire works.
It's one has to fail.
What if